Introducing concurrent mode. So, we're talking about ReactJS. ReactConf 2019 just happened, and now I'm reading the new docs. What do we got? Coming soon. Concurrent mode, which is experimental. Okay, so, first of all, caution. This page describes experimental features that are not yet available in a stable release. Do not rely on experimental builds of React in production apps. These features may change significantly and without a warning before they become a part of React. This documentation is aimed at early adopters and people who are curious. That's us. If you're new to React, don't worry about these features. You do not need to learn them right now. Okay. This page provides a theoretical overview of concurrent mode. For a more practical introduction, you might want to check out our next sections: suspense for data fetching, concurrent UI patterns, adopting concurrent mode, and concurrent mode API reference. So first, what is concurrent mode? Concurrent mode is a set of new features that help React apps stay responsive and gracefully adjust to the user's device capabilities and network speed. These features are still experimental and are subject to change. They are not yet part of a stable React release, but you can try them in an experimental build. Okay, blocking versus interruptible rendering. To explain concurrent mode, we'll use version control as a metaphor. If you work on a team, you probably use a version control system like Git and work on branches. When a branch is ready, you can merge your work into master so that other people can pull it. Before version control existed, the development workflow was very different. There was no concept of branches. If you wanted to edit some files, you had to tell everyone not to touch those files until you finish your work. You couldn't even start working on them concurrently with that person. You were literally blocked by them. This illustrates how UI libraries, including React, typically work today. Once they start rendering an update, including creating new DOM nodes and running the code inside components, they can't interrupt this work. We'll call this approach blocking rendering. In concurrent mode, rendering is not blocking. It is interruptible. This improves the user experience. It also unlocks new features that weren't possible before. Before we look at concrete examples in the next chapters, we'll do a high-level overview of new features. Okay, interruptible rendering. Consider a filterable product list. Have you ever typed into a list filter and felt that it stutters on every key press? Some of the work to update the product list might be unavoidable, such as creating new DOM nodes or the browser for performing layout. However, when and how we perform that work plays a big role. A common way to work around the stutter is to debounce the input. When debouncing, we only update the list after the user stops typing. However, it can be frustrating that UI doesn't update while we're typing. As an alternative, we could throttle the input and update the list when with a certain maximum frequency. But then on lower powered devices, we'd still end up with stutter. Both debouncing and throttling create a suboptimal user experience. The reason for the stutter is simple. Once rendering begins, it can't be interrupted. So the browser can't update the text input right after the key press. No matter how good a UI library, such as React, might look on a benchmark, if it uses blocking rendering, a certain amount of work in your components will always cause stutter. And also, often there is no easy fix. Concurrent mode fixes this fundamental limitation by making rendering interruptible. This means that when the user presses another key, React doesn't need to block the browser from updating the text input. Instead, it can let the browser paint an update to the input and then continue rendering the update list in memory. When the rendering is finished, React updates the DOM and changes are reflected on the screen. Conceptually, you can think of this as React preparing every update on a branch. Just like you can abandon work in branches or switch between them, React in concurrent mode can interrupt an ongoing update to do something more important, and then come back to what it was doing earlier. This technique might also remind you of double buffering in video games. Concurrent mode techniques reduce the need for debouncing and throttling in UI. Because rendering is interruptible, React doesn't need to artificially delay work to avoid stutter. It can start rendering right away, but interrupt this work when needed to keep the app responsive. Intentional loading sequences. We've said before that concurrent mode is like React working on a branch. Branches are useful not only for short-term fixes, but also for long-running features. Sometimes you might work on a feature, but it could take weeks before it's in a good enough state to merge into master. This side of our version control metaphor applies to rendering too. Imagine we're navigating between two screens in an app. Sometimes we might not have enough code and data loaded to show a good enough loading state to the user on a new screen. Transitioning to an empty screen or a large spinner can be a jarring experience. However, it's also common that the necessary code and data doesn't take too long to fetch. Wouldn't it be nice if React could stay on the old screen for a little longer and skip the bad loading state before showing the new screen? Yes, that would be good. While this is possible today, it can be difficult to orchestrate. In concurrent mode, this feature is built in. React starts preparing the new screen in memory first, or as our metaphor goes, on a different branch. So React can wait before updating the DOM so that more content can load. In concurrent mode, we can tell React to keep showing the old screen, fully interactive, with an inline loading indicator. And when the new screen is ready, React can take us to it. Concurrency. Let's recap the two examples above and see how concurrent mode unifies them. In concurrent mode, React can work on several state updates concurrently, just like branches let different team members work independently. For CPU-bound updates, such as creating DOM nodes and running component code, concurrency means that a more urgent update can interrupt rendering that has already started. For I/O-bound updates, such as fetching code or data from the network, concurrency means that React can start rendering in memory even before all the data arrives, and skip showing jarring empty loading states. Importantly, the way you use React is the same. Concepts like components, props, and state fundamentally work the same. When you want to update the screen, you set the state. React uses a heuristic to decide how urgent an update is, and lets you adjust it with a few lines of code so that you can achieve the desired user experience for every interaction. Putting research into production. There's a common theme around concurrent mode features. Its mission is to help integrate the findings from the human-computer interaction research into real UIs. For example, research shows that displaying too many intermediate loading states when transitioning between screens makes a transition feel slower. This is why concurrent mode shows new loading states on a fixed schedule to avoid jarring and too frequent updates. Similarly, we know from research that interactions like hover and text input need to be handled within a very short period of time, while clicks and page transitions can wait a little longer without feeling laggy. The different priorities that concurrent mode uses internally roughly correspond to the interaction categories in the human perception research. Teams with a strong focus on user experience sometimes solve similar problems with one-off solutions. However, those solutions rarely survive for a long time, as they're hard to maintain. With concurrent mode, our goal is to bake the UI research findings into the abstraction itself and provide idiomatic ways to use them. As a UI library, React is well positioned to do that. Next steps. Now you know what concurrent mode is all about. On the next pages, you'll learn more details about specific topics. Suspense for data fetching describes a new mechanism for fetching data in React components. Concurrent UI patterns shows some UI patterns made possible by concurrent mode and suspense. Adopting concurrent mode explains how you can try concurrent mode in your project. And concurrent mode API reference documents the new APIs available in experimental builds. Oh yeah. All right, let's check it out. Open it all in new tabs. Suspense for data fetching. Experimental. Caution, this page describes experimental features that are not yet available in stable release. Do not rely on experimental builds of React in production apps. These features may change significantly and without a warning before they become a part of React. This documentation is aimed at early adopters and people who are curious. That's me and you. If you are new to React, don't worry about these features. You don't need to learn them right now. React 16.6 added a suspense component that lets you wait for some code to load and declaratively specify a loading state, like a spinner, while you're waiting. For example, profile page, react.lazy, blah, 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 blah. Suspense, fallback, yada, yada. Okay. Suspense for data fetching is a new feature that lets you also use suspense to declaratively wait for anything else, including data. This page focuses on the data fetching use case, but it can also wait for images, scripts, or other asynchronous work. So, what is suspense exactly? Suspense lets your components wait for something before they can render. In this example, two components wait for an asynchronous API call to fetch some data. Okay, so we've got a resource, fetch profile data. And note this is happening outside of a component. So you've got your resource. Okay, so in your profile page, you've got a suspense wrapper with a fallback, loading profile. And then you've got profile details, which is defined down here. And then you've got a second suspense wrapper, loading posts, and then your profile timeline. So let's look at profile details. Here's profile details. So first, try to read user info, although it might not have loaded yet. So resource.user.read. So I'm assuming what happens here is that if this data is not available yet, it will suspend by throwing a promise. And then it will trigger this fallback here. And then this one here, profile timeline, will do the exact same thing. So try to read posts, although they might not have loaded yet. So, and we can try it on Code Sandbox. This demo is a teaser. Don't worry if it doesn't quite make sense yet. We'll talk more about how it works below. Keep in mind that suspense is more of a mechanism, and particular APIs like fetch profile data or resource.posts.read in the above example are not very important. If you're curious, you can find their definitions right in the demo sandbox. Let me open up a new window with this over on the side so you can look at the code while I read the rest of this. Oh, right, I can't affect font sizes separately, but whatever. Okay. Okay, good enough. Let me just smallify the font right quick so we can see more stuff. Okay. Okay, so here we go. All right. Suspense is not a data fetching library. It's a mechanism for data fetching libraries to communicate to React that the data a component is reading is not ready yet. Let me say that again. Suspense is a mechanism for data fetching libraries to communicate to React that the data a component is reading is not ready yet. So React can then wait for it to be ready and update the UI. At Facebook, they use Relay and its new suspense integration. They expect that other libraries like Apollo can provide similar integrations. In the long term, we intend suspense to become the primary way to read asynchronous data from components, no matter where that data is coming from. So, what suspense is not? Suspense is significantly different from existing approaches to these problems. So reading about it for the first time often leads to misconceptions. Let's clarify the most common ones. Suspense is not a data fetching implementation. Suspense does not assume that you use GraphQL, REST, or any other particular data format, library, transport, or protocol. Suspense is not a ready-to-use client. You can't replace Fetch or Relay with Suspense. But you can use a library that's integrated with Suspense, for example, new Relay APIs. Suspense does not couple data fetching to the view layer. It helps orchestrate displaying the loading states in your UI, but it doesn't tie your network logic to React components. That's an important one. What Suspense lets you do. So what's the point of Suspense? There's a few ways we can answer this. It lets Suspense lets data fetching libraries deeply integrate with React. If a data fetching library implements Suspense support, using it from React components feels very natural. Suspense lets you orchestrate intentionally designed loading states. It doesn't say how the data is fetched, but it lets you closely control the visual loading sequence of your app. Suspense helps you avoid race conditions. Even with await, asynchronous code is often error-prone. Suspense feels more like reading data synchronously, as if it was already loaded. Using Suspense in practice. At Facebook, so far, they have only used the Relay integration with Suspense in production. If you're looking for a practical guide to get started today, check out the Relay guide. It demonstrates patterns that have already worked well for them in production. The code demos on this page use a fake API implementation rather than Relay. This makes them easier to understand if you're not familiar with GraphQL, but they won't tell you the right way to build an app with Suspense. This page is more conceptual and is intended to help you see why Suspense works in a certain way and which problems it solves. What if I don't use Relay? If you don't use Relay today, you might have to wait before you can really try Suspense in your app. So far, it's the only implementation that we tested in production and are confident in. Over the next several months, many libraries will appear with different takes on Suspense APIs. If you prefer to learn when things are more stable, you might prefer to ignore this work for now and come back when the Suspense ecosystem is more mature. You can also write your own integration for data fetching library, if you'd like. For library authors, we expect to see a lot of experimentation in the community with other libraries. This is one important thing to note for data fetching library authors. Although it's technically doable, Suspense is not currently intended as a way to start fetching data when a component renders. Rather, it lets components express that they're waiting for data that is already being fetched. Unless you have an idea for a solution that helps prevent waterfalls, we suggest to prefer APIs that favor or enforce fetching before render. The current documentation for Relay Suspense API doesn't yet dive deep into preloading, but we plan to publish more about these techniques in the near future. Our messaging about this hasn't been very consistent in the past. Suspense for data fetching is still experimental, so you can expect our recommendations to change over time as we learn more from production usage and understand the problem space better. Traditional approaches versus Suspense. We could introduce Suspense without mentioning the popular data fetching approaches. However, this makes it more difficult to see which problems Suspense solves, why these problems are worth solving, and how Suspense is different from the existing solutions. Instead, we'll look at Suspense as a logical next step in a sequence of approaches. Fetch on render. For example, fetch in useEffect. Start rendering components. Each of these components may trigger data fetching in their effects and lifecycle methods. This approach often leads to waterfalls. Fetch then render. For example, Relay without Suspense. Start fetching all the data for the next screen as early as possible. When the data is ready, render the new screen. We can't do anything until the data arrives. Render as you fetch. For example, Relay with Suspense. Start fetching all the required data for the next screen as early as possible, and start rendering the new screen immediately before we get a network response. As data streams in, React retries rendering components that still need data until they're all ready. Note, this is a bit simplified, and in practice, solutions tend to use a mix of different approaches. Still, we will look at them in isolation to better contrast their trade-offs. To compare these approaches, we'll implement a profile page with each of them. Approach 1, render on fetch, not using suspense. A common way to fetch data in React apps today is to use an effect. In a function component, fetch something. Or in a class component, fetch something. We'll call this approach fetch on render because it doesn't start fetching until after the component has rendered on the screen. This leads to a problem known as a waterfall. Consider these profile and timeline profile components. So we've got fetch user, then set user, and then fetch posts, then set posts. If you run this code and watch the console logs, you'll notice the sequence is we start fetching user details, we wait, we finish fetching user details, we start fetching posts, we wait, we finish fetching posts. If fetching user details takes 3 seconds, we only start fetching the posts after 3 seconds. That is a waterfall, an unintentional sequence that should have been parallelized. Waterfalls are common in code that fetches data on render. They're possible to solve, but as the product grows, many people prefer to use a solution that guards against this problem. Approach 2, fetch then render. Libraries can prevent waterfalls by offering a more centralized way to do data fetching. For example, Relay solves this problem by moving the information about the data a component needs to statically analyzable fragments. Okay. By moving the information about the data a component needs, so each component needs some amount of data, Relay, you define that as a fragment that is statically analyzable, and then later all those fragments get composed into a single query. On this page, we'll assume knowledge of Relay. So we're going to be using this in our example. Instead, no, in this page we don't assume knowledge of Relay, so we won't be using it in this example. Instead, we'll write something similar manually by combining our data fetching methods. Okay, so fetch profile data. You've got a promise of all fetch users and posts. In this example, profile page waits for both requests but starts them in parallel. So you kick off fetching as early as possible. Okay, so you start fetching the profile data, which gives you a promise. Then you've got your profile page here. And then use effect. So when the promise is done, then you set the user and the posts. So this renders loading profile until both the users, or until the user data is ready. And then once the post data is ready, it passes the post data into the post profile timeline component. And then if the posts aren't ready, it renders loading posts until that's ready and passes it on. Okay. The event sequence now becomes something like we start fetching user details, we start fetching posts, we wait, we finish fetching user details, we finish fetching posts. We solved our previous networked waterfall, but accidentally introduced a different one. We wait for all data to come back with promise.all inside of fetch profile data. So now we can't render profile details until the posts have been fetched too. We have to wait for both. Of course, it's possible to fix this. This is possible to fix in this particular example. We could remove the promise.all call and wait for both promises separately. However, this approach gets progressively more difficult as the complexity of our data and component tree grows. It's hard to write reliable components when arbitrary parts of the data tree may be missing or stale. So fetching all data for the new screen and then rendering is often a more practical option. Approach 3, render as you fetch. using suspense. In the previous approach, we fetched data before we called setState. Start fetching, finish fetching, start rendering. With suspense, we'll start fetching first, but we flip the last two steps around. Start fetching, start rendering, finish fetching. With suspense, we don't wait for the response to come back before we start rendering. In fact, we start rendering pretty much immediately after kicking off the network request. Okay, so this is not a promise. It's a special object from our suspense integration. So we've got a resource, whatever that is. So in the profile page, we get down here. So okay, so here's what happens when we render profile page on the screen. We've already kicked off the requests in fetch profile data. So when we do this, this kicks off the actual requests outside of rendering. It gave us a special resource instead of a promise. In a realistic example, it would be provided by our data library's suspense integration, like relay. 2, React tries to render profile page. So here it is trying to render profile page. It returns profile details and profile timeline as children. Here we go. React tries to render profile details. Here we go. It calls resource.user.read. None of the data is fetched yet, so the component suspends. React skips over it and tries rendering other components in the tree. So it skips over that, tries rendering other components in the tree. React tries to render profile timeline. It calls resource.posts.read. Again, there's no data yet, so this component also suspends. React skips over it too and tries to render other components in the tree, but there aren't any. There's nothing left to try rendering because profile details suspended. React shows the closest suspense fallback above it in the tree, loading profile. We're done for now. This resource object represents the data that isn't there yet, but might eventually get loaded. When we call read, we either get the data or the component suspends. As more data streams in, React will retry rendering, and each time it might be able to progress deeper. When resource.user is fetched, the profile details component will render successfully and will no longer see the loading profile. Fallback. Eventually, we'll get all the data, and there will be no fallbacks on the screen. This has an interesting implication. Even if we use a GraphQL client that collects all data requirements in a single request, streaming the response lets us show more content sooner. Because we render as we fetch, as opposed to after fetching, if user appear in the response earlier than posts, we'll be able to unlock the outer suspense boundary before the response even finishes. We might have missed this earlier, but even the fetch on then render solution contained a waterfall between fetching and rendering. Suspense doesn't inherently suffer from this waterfall, and libraries like Relay take advantage of this.